All right, welcome back. We are now moving into our next topic, which is section number 15, examining wireless deployment options. We have lots and lots of choices with regard to how we decide to deploy a wireless solution within our enterprise. We talked in the previous section about the different radio principles that we would have to consider. For example, what types of IEEE standards am I going to implement? And then within the standard itself, what types of features am I going to implement to enhance the productivity and enhance the ability of the clients to communicate over the wireless network. But you also have different design capabilities, different form factors of APs, different types of antennas, different deployment options. Are we going to go with a premise-based solution? Are we going to go with a cloud-based solution? And so on. Is it going to be an autonomous solution? Is it going to be a hybrid solution? Are we going to have a wireless LAN controller or virtual wireless LAN controller, and so on? So we do have lots and lots of choices with regard to how we're going to do our deployment. So this whole section is really about those concepts, right? We're going to take first a look at different wireless deployment overviews, or at least different wireless deployment options from an overview perspective. We'll talk about autonomous AP deployment and how that might be beneficial or generally considered legacy. We'll also talk about centralized Cisco wireless LAN controller deployments, what the architecture is, what the options are for deploying what we call lightweight access points in a centralized, centrally managed environment. And then we'll also talk about the FlexConnect deployment options, which was previously called REAP or HREAP. We'll talk about cloud deployments and how those cloud deployments can either benefit us or limit us in our capabilities with regard to wireless deployments. We'll talk about the cloud-based Meraki solution. We'll also take a look at the Cisco Catalyst 9800 series controller. What are the deployment options with that controller specifically? And then we'll talk about Cisco Mobility Express. And that'll be it for this section. We'll wrap it up with a quick summary challenge, and then we'll move on to roaming and location services, and then details about AP operation, authentication, and troubleshooting. All right, so let's go ahead and get started. When it comes to deploying a wireless solution, and again, this is not really Cisco specific. There are a lot of vendors that provide a lot of options with regard to deploying wireless. And I think for the most part, these solutions exist from multiple vendors. But from a Cisco perspective, we have basically 5 different deployment options that are available. We can use autonomous APs, which basically act as standalone access points with their own logic and their own interface and control. A centralized deployment within the enterprise, right? Centralized over the intranet, meaning within our corporate network, typically using what we call Cisco Unified Wireless with a Cisco Wireless LAN controller. We have FlexConnect options as well. We'll talk about that in quite a bit of detail in this section. We have software-defined access options using an overlay and an underlay switching fabric that allows us to define the operation and the function of our network by using software-defined architectures. And then we also have our 100% cloud-based managed solutions. When it comes to autonomous APs, typically these are going to be access points that you're going to be deploying in a small office or maybe a hotspot type of location, something that is a much smaller enterprise type of environment. Each individual access point is managed separately. It has its own firmware, it has its own configuration, it does all of its own authentication and association requests directly on the access point itself, and even terminates the traffic from the clients directly on the trunk link that would be connected to that particular access point. We do have an advantage here. We can, if we only have 2 or 3 access points in our entire office, we can reduce our costs significantly without increasing the amount of management and the amount of overhead required to manage, just a small set of access points. So it's very simple to deploy. It is extremely cost effective, but as the solution grows, as we have more and more clients, as the spectrum gets more and more complicated with both Wi-Fi and non-Wi-Fi interferers, we tend to try to look at more of a converged solution so we can manage all aspects of the wireless environment. And that's what a centralized deployment model is. All the traffic is centralized. The APs can connect anywhere in the enterprise as long as they have reachability to the wireless LAN controller. And we'll talk about this architecture and the individual protocols like DTLS, CAPWAP, and so on that are involved in this type of deployment. How do the access points provision themselves? How do they update their firmware? How are security policies propagated? And so on. Another option in the middle here, FlexConnect. This is typically used in a location where you might have remote offices or branch offices, and you may still have kind of a small number of access points, but so you don't necessarily need a wireless LAN controller per se, but we still want to be able to control where the traffic is routed, right? So the wireless LAN data traffic can either be tunneled back to a controller, what we call a central switching option, or the data traffic can be broken out locally on the wired interface, which is the local switching option. And we would make these decisions based on the type of traffic. Does it make more sense to route the traffic locally, or does it make sense to send it back to the controller? With the SD access solution, we're obviously integrating our wireless connectivity using the software-defined access architecture. And we're kind of moving away from what we would traditionally call a VLAN-centric architecture to policy-based and group-based enterprise architectures, but adding this extensibility into layer 2 so that we can propagate and manage and utilize the software-defined architecture that provides us that software-defined flexibility. And then finally, the cloud-based solution where we might have either virtual controllers with Cisco Meraki or the 9800 series cloud controller. Both of those things we'll talk about in quite a bit of detail later on. Still provides centralized management, but we don't necessarily have to have the infrastructure to support the connectivity. It scales very well for small networks all the way up to very large networks. And overall, it's going to reduce our cost, potentially, if it's deployed correctly, and it will reduce the number of IT staff from the perspective of we don't have to have IT specialized individuals at each location to manage these devices. Even rollouts and deployments can be done in an automated fashion, right, by using plug-and-play provisioning and so on. And certainly we'll talk about the cloud options as well. All right. So quick question, which type of wireless deployment is appropriate for hotspots or small enterprises? That would be autonomous. All right. Now, that's not to say that you couldn't deploy a controller in these types of environments. Some of the smaller controllers are relatively cost effective. They do provide basically the same AirOS functionality that you would see in some of the larger controllers. And they scale down to about 25 to 30 access points. So there is a place for converged, or excuse me, unified wireless in these types of environments. Now, the first model that we'll take a look at is autonomous access point deployment. Basically, in this particular case, each access point is operated and managed independently of any other device in the architecture. Right, so each of these APs operate independently. They're each managed independently. They do not have any, even on the spectrum side, any real knowledge of each other. At least not from like a radio resource management perspective, where access points are providing telemetry information to a central controller, and then the central controller is managing those APs, spectrum, based on what's being reported by the access points themselves. All right. The biggest benefit that we have with this type of deployment is that if you only have a handful of access points, it's a really, really cost-effective way to extend your network into the wireless world. This is the kind of deployment that somebody might use at a home office or a very small office that might only have, you know, a floor of cubicles and so on. All right. If you want to deploy this, it is generally recommended that you have maybe up to 5 or 6 or 7 access points in this type of environment. When you start to get more than that, start to get upwards of 10 or 20 or 30 access points, even though that might be considered a relatively small deployment from an enterprise perspective, the cost benefits kind of are outweighed by the ability to manage those access points from a central controller, manage security policies, manage the spectrum, and so on. All right. In these types of deployments, generally the clients will connect to the AP that has the highest RSSI and has the lowest or highest signal-to-noise ratio, and they'll communicate over the network through that access point. We can still provide roaming services. It's not as seamless as maybe the mobility services that you would see in a converged environment or a unified wireless environment, but you still have that capability of roaming from one access point to the next. Now, that doesn't mean the roaming would be necessarily seamless, right? Authentication from one AP is not, or authentication credentials and information and status is not going to be transmitted to other access points in the environment. But if your client, so if you're on an active voice call, or if your client is in an active, TCP related session or whatnot, it is possible and likely that those connections would drop as you try to reassociate as you roam from one AP to the next. There are some benefits to autonomous, but there are also some limitations, right? The benefits include things like lower CapEx or lower capital expenditures, very suitable to small deployments where you have only a handful of access points per location. You have several features that you can still implement, things like DHCP and radius connectivity and databases for authentication, but maybe not as robust as what you would see in a unified wireless type of world. Also, you still get, to an extent, some spectrum management, right? Access points can identify if a particular frequency or a particular channel is congested with either Wi-Fi or non-Wi-Fi interferers, and it can make a decision on what channel to move to based on that information that it's observing itself in the wireless environment. Now, there are some limitations as well. Obviously, the biggest limitation would be that each access point has to be managed separately. So you can have some security inconsistencies, you can have wireless SSID or VLAN inconsistencies, user authentication inconsistencies, and so on. Also, the firmware and the software of the access points needs to be managed independently. So this can be difficult if you're rolling out perhaps a new fix for a bug, or you just simply want to upgrade your access points. You can have some scalability issues from that perspective, at least from a management perspective. For Wi-Fi functionality, probably the biggest loss, and in my opinion, is the most significant detriment to this particular model, is you have no radio resource management, no ability to do coverage hole detection, to manage rogue access points, to manage the spectrum from a transmission power control level or dynamic channel assignment perspective, and so on. So that's definitely a big limitation. Also, you don't get advanced security concepts, right? You're not going to be able to identify rogues and mitigate the effect of rogues in that environment. WIPS, or wireless intrusion prevention, is not going to be available. And guest access, even though it can be facilitated, again, not centrally managed and not easily managed in an autonomous environment. All right. And as I mentioned previously, you just don't get the fast, secure, seamless roaming that we always talk about when it comes to unified wireless. There is a mechanism called WDS, which allows us to exchange roaming client credentials among APs that are in the same subnet. So we can kind of get some semblance of seamless roaming with WDS, but that would mean that those access points would have to be in the same broadcast domain, and the outside of that broadcast domain, that wouldn't work. All right. All right. As far as autonomous configuration goes, very, very simple. You're going to provision the APs independently. They're going to have VLAN IDs that are tied to SSIDs. You're going to have a bridged virtual interface that's going to be your trunk connection to your switch. There is no kind of DTLS type of configuration or CAPWAP consideration because we're not communicating to a wireless LAN controller. But you do have all the other functions, right? You have the ability to do advanced enterprise security with WPA2. You can modify transmit power levels and channel assignments. You can even implement dynamic channel assignments on the AP based on what it sees in the local spectrum. And you can adjust the overall power of the dBm of the access point so that you're not broadcasting, if you will, wireless signals outside of the intended BSA or the intended coverage area. Okay, so this diagram here talks about really how an autonomous AP interacts with a client and how it communicates to a client. So A, wired to wired client traffic. That's the red line in this particular diagram. Wired to wired traffic. Well, let's actually say wireless to wired traffic, right? Even though the red line depicts wired to wired, you still have the wireless clients behind the APs that are trying to communicate. So if I'm going wireless to wired, that's going to go through the AP. It's going to be handed off on the trunk interface that is directly attached to the access point, typically a trunk. It doesn't have to be a trunk, but it would typically be a trunk if you had, for example, multiple SSIDs, and each SSID would then be tied to a particular VLAN. All right. So the AP itself, regardless of whether it's unified or autonomous, is going to be responsible for converting those 802.11 frames into an 802.3 Ethernet frame or an Ethernet 2 frame, and then sending that frame to the local access switch that the access point is connected to. This differs significantly from a traditional unified wireless architecture where client traffic is tunneled or sent back to the controller, and then the controller will hand off that traffic on its local connection wherever the controller is physically located. All right. Traffic from wireless clients to wireless clients, if they're connected to the same AP, in the same VLAN, etc., sometimes in different wireless LANs, or even on a different radio, so a 2.4 gigahertz client to a 5 gigahertz client, they go from one client to the other client directly through the AP. They don't actually even traverse the AP connection to the switch. It doesn't create any load on the switch, obviously, because it's not going to be sending traffic to the switch. But if both clients are in different VLANs and different wireless LANs, if they're on the same radio or on different radios within with a different wireless to VLAN mapping, the AP is not allowed to route clients between those VLANs because APs operate at layer 2 of the OSI model, whereas routers clearly operate at layer 3 of the OSI model. In order for me to go from one VLAN to another, the traffic has to be routed. So the AP has to forward that traffic coming from the client into the LAN until it reaches a layer 3 device, and then that layer 3 device will forward the packet to the second client in the appropriate subnet, and the traffic will be traversed back to the AP. All right, so each client is going to communicate with the other clients as if the client was on the LAN behind a particular router. Clients are actually not going to see each other in the same wireless space, even though they might be using the same general radios or the same general frequency to communicate. Lastly, traffic that from clients sent or clients sending frames to other clients that are connected to other APs. Clearly, that's going to have to transition through our wired infrastructure and AP to AP communication is going to go through the wired network. Now, it is possible to do direct AP to AP communication, but it's not actually nearly as efficient as transmitting through the wire because, again, the wireless side is half duplex in most cases, and that half duplex communication is not going to be nearly as efficient. All right. So the data flow type does have kind of an impact on the overall network design, right? It is a consideration to take into account. All right. If you're doing a wireless device to wireless device communication, and those wireless devices are attached to different access points in the infrastructure, you might see a heavy amount of traffic on that wired infrastructure because they may not they're not in the same wireless LAN or the same subnet. Routers have to be involved and so on. Okay. Now let's kind of flip that script a little bit and talk about that from a unified perspective. Because different APs, even in different subnets, are associated to the same controller, we can actually gain efficiency by using a unified wireless design because that controller traffic stays within the controller, right? It doesn't necessarily have to be passed outside of the controller. There are some exceptions to that, obviously. We'll talk about that when we get into the next section, which is describing a centralized Cisco wireless LAN controller deployment. Okay? What are 3 limitations to the standalone AP design? Prone to configuration inconsistencies. Yes, if you have complex configs and a larger number of access points. Fast, secure roaming between sites, subnets is not possible. No rogue detection and mitigation. We did talk about that specifically. Cannot be converted to a controller-based AP. That's not true, actually. By modifying the firmware, you can actually convert an autonomous AP to a controller-based lightweight access point. Must be configured via the CLI. That's also actually not true. Most of these access points have some sort of graphical interface that you can access to do a GUI-based configuration. Difficult to manage in small or home offices. No, actually, this is the place where you might actually see it. So fast, secure roaming between subnets is not possible. And we talked about that in the lecture portion here, and that makes sense. All right. So now let's get into talking about a centralized Cisco wireless LAN controller deployment. This is probably what in most modern enterprise wireless infrastructures you're going to see as the primary deployment model, right? It's sometimes referred to as unified wireless. Sometimes it's referred to as converged wireless, although from a Cisco perspective, converged wireless actually means something really kind of completely different. But what we talk about, and I'll probably mention briefly later on what converged wireless references, but we'll talk right now about the unified wireless architecture, which really involves the use of some sort of Cisco wireless LAN controller. That controller is running AirOS that is responsible for configuration, control, management of our access points, the radio frequency spectrum or the airspace, rogue detection, security, pretty much all aspects of our wireless LAN deployment. All right. Now, comparing this to, say, an autonomous access point deployment, the centralized architecture, those APs do not function independently, right? They have actually pretty reduced functionality in the access point, with maybe some basic split MAC features. We talked about some of the split MAC functions in the previous section to manage some of the real-time aspects of wireless as opposed to the less time-sensitive aspects of wireless. But depending on how the wireless LAN controller is configured, how we manage those APs and so on, there is certainly a lot, the implementation is going to be a lot different than what you would see in a truly autonomous system environment, right? In this particular architecture, the unified wireless architecture, the functionality of the wireless network is split between the access points and the wireless LAN controllers, which are part of essentially our infrastructure, if you will, the controller itself. It could be really placed anywhere inside of our infrastructure as long as the access points have the capability of communicating to that wireless LAN controller, and the necessary protocols and functions are supported by the infrastructure. And we'll get into more in-depth discussion about what those protocols might be, what kind of services we might be running within our unified wireless, and so on. So when we talk about the split MAC function, like I said, we did talk about this previously, but the access point generally in a split MAC architecture handles all of the real-time MAC functionality. That's our media access control functionality, and all the non-real-time MAC functionality is going to be processed by the wireless LAN controller, right? So authentication and association, any type of management of the wireless frames themselves and so on, that's going to be part of the real-time functionality. All right, the actual configuration, deployment of the SSIDs, the security posture that we decide to take, that's going to be a function of the controller. Now, the primary advantage of running this centralized architecture, I think there are some pretty obvious points, right? It gives you as an administrator kind of a control or centralized control of your entire AP infrastructure. You might have hundreds or even thousands of access points, and you can manage them from one interface. You certainly will understand that there's got to be some consistency in configuration, firmware deployments, security deployments, wireless LAN deployments, and so on. And that's definitely achieved through the unified wireless architecture. So we have really this ease of management in very, very large deployments. The APs themselves have visibility and awareness of all of the access points that they're adjacent to or that they're in proximity to. And that's going to provide additional functionality like radio resource management, dynamic radio resource management, coverage hole detection, rogue access point discovery and containment, and so on. All right. So the controller itself can be informed actually, and that's the coverage hole reference that I made. If an AP becomes faulty, right, it goes down. All the other APs around that access point can now adjust their power levels to compensate for that black hole or that coverage hole in our wireless network. The wireless LAN controller can offload wireless clients to a neighboring AP if that particular AP becomes overloaded. In an autonomous scenario, really the decision about which access point that I'm going to connect to outside of any kind of actual static security would be basically the RSSI and the SNR values, right? So we're going to basically connect to whichever access point provides us the highest quality signal. But within a unified wireless architecture, I can say, you know what, this access point is already servicing, 100 clients, and that's reducing the amount of throughput from that AP's perspective on the wireless side. So let's go ahead and force additional clients to go ahead and associate to neighboring APs, even though they might have, a smaller RSSI or a lower SNR value. We would, but they're still those variables or those properties are still well within the threshold of providing adequate service to those clients. Let's go ahead and just instruct them to go ahead and associate to those less busy or less loaded access points, right? So load balancing, self-healing properties, ease of management, scalability really is a huge factor as well. These are all big benefits to the unified wireless architecture, okay? So the wireless network design, is going to incorporate some additional points or additional components that you're not going to see in a traditional autonomous or standalone access point environment, right? The centralized architecture is going to require, of course, the wireless LAN controller, maybe possibly multiple controllers if we're doing some sort of guest attachment or we have some sort of redundancy and failover. It'll probably require at least some sort of back-end Active Directory integration, some sort of back-end LDAP directory, and maybe possibly some other elements as well. Certainly we'll have all of our infrastructure components, which we would have really anyway if we even had autonomous access points. All right? So when would it be good to decide when to use a unified wireless environment? Well, quite frankly, most of the time it's going to be beneficial, right? In fact, just about every vendor offers, every serious wireless vendor offers some sort of unified wireless solution in their product suites, right? Some of it's virtual, like the Aruba platforms from Aruba, HP/Aruba. They use a virtual controller scenario. Cisco uses a physical controller or cloud-based controller. But in the end, it's really about providing the same types of benefits, right? So the general rule is, of course, if you have a very large campus, large manufacturing plant, hospital, university or educational type of campus, if you have significant needs of security and customization of the access points, if you're implementing advanced services like voice over wireless LAN or video over wireless LAN, those types of things, yes, you certainly would consider using a unified solution because of all the benefits of the incorporated technology and really the visibility of the airspace in that with that unified solution that it provides, But even in my own house, I run a 2504 controller running AirOS, and I've got a couple of different Cisco APs around the property. But it is quite cost effective, actually. Surprisingly not that expensive for a small controller that really pretty much runs all of the same software that a large enterprise type solution would run. So I encourage you to take a look at it regardless of the size of the enterprise. Okay? So what you're seeing in this diagram, I've already kind of made reference to a few of these points. Obviously the CapWAP access points, which are lightweight access points using that open standard CapWAP protocol with DTLS tunnels to talk to the Cisco wireless LAN controller. And then you have your other infrastructure elements like switches and routers and so on. If you're running voice over wireless, you certainly might have some sort of voice over IP or unified communications platform like Call Manager, IP phones, mobile users, and so on. We will talk actually about the mobile solution a little bit later on. That's one of the last things that we'll talk about in this section here, Mobility Express. But there's, obviously the two key components in this diagram are the access point itself and the wireless LAN controller. And there are many, many different access points to choose from. Indoor, outdoor, dual band, multiple input, multiple output, AC, N, AX even, and so on. So integrated antennas, external antennas, all kinds of options. All right. So what are some of the benefits and what are some of the limitations? One of the benefits, of course, I've already kind of talked about is centralized management, the ability to troubleshoot effectively from a single point, not only attachments of APs, but the clients themselves. You get a lot of visibility across your entire enterprise in one portal to see what kind of clients are attached to the network, how they're authenticating, how much traffic they're generating, what types of traffic they're generating, and you can apply QoS policies, enterprise-wide QoS policies, and so on, which reduces your total cost of ownership because, again, you're not managing, at least from a billing perspective or a time perspective, you're not managing hundreds or thousands of access points independently. Could you imagine, for example, if Cisco released a firmware for a particular AP and said, hey, you guys need to upgrade to this firmware because there's a serious bug in the current version that you're running. And you have to now go do that individually on each of those access points. That's going to take a lot of time, which of course directly results in man hours, which is dollars. Which brings us to the second point, right? Very easy to deploy. Most of these access points are basically just plug and play. They will self-provision based on some enterprise-wide parameters that you might configure, what we call priming the APs, or even allowing them to self-provision. Even from a geolocation perspective, Cisco does now ship a lot of their access points which are not localized to a specific country or a specific region, and then you can use some tools to actually provision that AP because there are different regulations and different types of standards in different areas of the world. So very easy to deploy, very easy to manage. You're going to get that consistent configuration because really there's only one configuration, and that is the configuration on the controller. That has to do also, by the way, with firmware, right? Upgrading that software on those APs is going to be simple because you're basically going to push out or provision the firmware upgrade directly from the controller. One of the most critical things, I think, which we see listed here, is radio resource management. The ability to get complete visibility of the spectrum, how the spectrum is being utilized, not only its intended use, right? The types of APs we have, the channel selection that we're using, the transmission power of each of the access points, and so on, right? We have to create essentially this mesh of wireless coverage, and if every AP is reporting their position and reporting their current status to the controller, it's going to be much easier to manage that mesh. But we're also talking about other aspects, right? We're talking about rogue detection and mitigation, a couple of bullet points down, the ability to identify over the air or even within the wired LAN attached rogues in the network. And then we can mitigate by containing those devices and so on. But we also talk about managing the spectrum from a much more visible component. There's a YouTube video that we have that talks about spectrum analysis and spectrum expert and how Cisco has so much more visibility into what the spectrum looks like. When we talk about a wireless spectrum, we're not just talking about a .11 wireless spectrum. We're talking about anything that sits in that frequency range, both other Wi-Fi interferers that might interfere, but also non-Wi-Fi interferers, which might have a very specific pattern. They have a very specific kind of signature, if you will, right? We can tell what a microwave looks like. We can tell what a DECT phone looks like, or a Bluetooth device looks like, and we can take action, right? And then we can even report that back to an overall manager of our wireless environment, generate heat maps, and kind of self-heal if we see some of that stuff happening. There's a video on our YouTube channel that talks all about that, actually, in our wireless group. All right. High availability, of course, that's always something that we concern ourselves with when we're talking about a reliable enterprise network. APs can fail each other over. We have single sign-on capabilities. Not only that, but we also have the ability to even deploy controllers in a redundant fashion. So one controller can take over for the other. We can also load balance dynamically, like I mentioned before, and so on. WIPS, integrated security. WIPS is wireless intrusion prevention. Identity networking, specifically really just Cisco Identity Services Engine, right? They mentioned a couple of things here. Identity networking is all about network access control, being able to identify who's attaching, what the attachment point is in the network, what the posture and the profile of a particular device is that's actually utilizing the wireless network, and then we can make decisions on how that user is going to be able to interact with the network. Are they going to get full access? What VLAN are they going to be assigned to? What kind of ACL is going to be applied to their profile via a downloadable ACL? Is there some deficiency in their current configuration that would prevent them from getting full access? So we can do remediation. We can say, okay, you don't meet the standard for connecting to our enterprise network, but if you do XYZ, we will go ahead and reevaluate you, and we can then do a change of authorization. So we're going to give you some limited access right now, which will provide you the ability to remediate, and then come back and check with us. And after you come back and checked with us, we can then go ahead and change the authorization to the full enterprise access or whatever it might be, right? Voice and data over wireless LAN, seamless roaming, very, very important concept, particularly when it comes to voice, with the limitations or the specific requirements that voice has to be able to function effectively over the network. Location-based services are getting much, much better, especially when the access points can talk to each other and they can report information. We can still do good triangulation to be able to identify where a device is located, secure guest access beyond just simply providing a basic guest SSID with some basic security. We can do captive portals. We can provide tunneled access to the DMZ of our network for internet-based access, so they're not actually routing or attaching themselves to our corporate network, and so on. The ability to create a mesh, which really, quite frankly, most wireless networks are to an extent, but a mesh takes it one step further, where we have intelligent routing across multiple access points that might be acting in bridged mode, highly customizable and advanced feature sets. Well, all this stuff we've been talking about really is that advanced feature set, right? The ability to do all of these things, all right? Now, they do list some limitations here as well. The limitations of deploying a centralized architecture: all end user traffic is forwarded towards the wireless LAN controller. I take exception to that a little bit, because there is a feature called FlexConnect that doesn't require that to happen. But generally, when you are deploying, especially in an enterprise LAN or MAN, if you're deploying a wireless LAN controller, yes, the traffic generally would be sent back to the wireless LAN controller and then handed off to the infrastructure from a group of interfaces that are connected on the controller. All right. Poor use of the LAN and WAN infrastructure when internal resources are distributed. That kind of goes to the previous point, right? Because all the traffic is being sent to the controller, and then the controller is handing off that traffic, that means we don't really have the ability to do what we call intelligent routing and nearest service-based routing and so on. The wireless LAN controller can become a bottleneck, again, all related to the first point, and it can become a single point of failure. CAN is the operative term here, right? If you're doing link aggregation and you're deploying multiple controllers throughout your enterprise and you're doing adequate load sharing across those controllers, you can design out those bottlenecks, right? Same thing with the single point of failure. We can create these redundancy groups in the unified wireless architecture that ensures that if a controller fails, another controller can take over and so on. All right. So generally speaking, the autonomous system just really doesn't provide any of these functions. And even if it does provide some of them, they're not really done that well. So a unified wireless architecture is really where you'd like to be, right? And I think that's why you see in most enterprise solutions, even small to ginormous, right? You're going to see these unified wireless options, okay? So let's start by talking about how do we do centralized control and provisioning of our access points. The first thing that has to happen is the AP needs to connect to the infrastructure. Now, generally, it is going to have at least one communication path to the controller via a management IP address, right? And there are different interfaces. We'll get into the specifics of that later on, but there are different interfaces on a controller, some that we can create, some that are created by default, but there's always a way for the access point to essentially be able to communicate not only for registration, but also for passing the client traffic back to the controller. One might be an interface, a dynamic interface that you create, which is tied to a VLAN. The other might be a service interface or a management interface for managing the AP process of joining the controller and so on. But nonetheless, it all goes back to the controller. So however you decide to provision that controller, whether it's by pre-priming the controller or using some sort of discovery mechanism through broadcasting or DHCP or DNS or whatever it might be, the AP is going to ultimately join the controller. Now, once that occurs, some of those 802.11 frames, that MAC functionality, media access control functionality, is going to be split between the controller and the access point. And we've mentioned this already one time before, right? All of the real-time functionality is going to typically reside on the access point, and then all the non-real-time functionality is going to be processed at the controller. All right. We call this split MAC mode, and really the benefit of operating with the split MAC architecture comes with mobility and the ability to move through the enterprise without losing connectivity, without losing your association and authentication status. Now, CAPWAP is the protocol of choice for communicating between the wireless AP and the control. Now, we don't need to get into the specifics of the control and provisioning of wireless access points protocol, but I do want to at least give you some information about it, right? It is a standard. Obviously, it's going to allow our central wireless LAN access controller, or AC, to manage our wireless termination points, which are our WTPs. I'm speaking generically, of course, from the protocol's perspective, which are our wireless access points in this particular case. CAPWAP is actually fairly new RFC, RFC 5415, if you want to go reference that and take a look at it in more detail. But it is a lightweight access point protocol, what we call LWAPP, not to be confused with Cisco's actually that's what they're referencing in this particular case, because Cisco had originally come up with, or at least acquired through acquisition, this lightweight access point protocol. All right, so CAPWAP kind of became the open standard version of that, right? So the state machine in CAPWAP is really similar to LWAP, but they've added this functionality of DTLS, the tunnel establishment that we see with the datagram transport layer security. The standard itself, the CAPWAP standard itself, provides for configuration management, device management, allows for configurations of the devices and firmware to be pushed out to the access points, but it is largely the same as the LWAP finite state machine, all right? So if you were to go and study LWAP or LWAPP and take a look at that and then kind of compare and contrast that to what we see with CAPWAP, CAPWAP, you would see it's pretty similar, all right? The protocol does use an encapsulation and transport mechanism, and it is completely generic, right? So it's completely independent of any specific radio technology. So we don't care what we're binding to on the backside. 802.11 binding is documented in RFC 5416, and it talks about that. CAPWAP as a protocol runs over UDP as the transport. The control channel is UDP port 5246, and the data channel is UDP port 5247. So it's kind of just a very brief introduction of CAPWAP as a protocol. Again, we don't in this particular class, these are not the CCNP wireless specific courses, so we're doing kind of a high-level overview of all this stuff, so we don't get into it in much more detail than that. Okay, it is an IETF RFC-based protocol. As I mentioned, I gave you the RFC numbers. Access points can be either pre-provisioned with the controller information, or they can use various mechanisms to discover the actual controller. There's a broadcast mechanism. There's a mechanism of identifying the controller by some options in DHCP, and also DNS information. All right. But once that takes place, the CapWAP control messages get exchanged between the wireless LAN controller and the AP, to do things like controller discovery, to do join processes, to get the AP's configuration, to push firmware to the access point from the controller, to gather statistics about the radio side of the house, right? The radio resource stuff. And then also the wireless security enforcement, depending on what type of wireless security we've implemented. We also can use those control messages for station access, authentication components, mobility components, and like I said, really gather statistics about the wireless network, provision wireless security, and so on. As I mentioned previously, there are two distinct planes of existence with CapWAP. CapWAP differentiates specifically between the control plane and the data plane, right? We can see a green box, if you will, or green pipe that represents the data plane. Think of the data plane functionality as just really the .11 frames that are being sent by the client to the infrastructure, whereas the control plane is the provisioning component, the management of the radio, the spectrum, and so on. Okay? So there are actually two modes of operation in CapWAP, the protocol itself. We can do split MAC in a centralized mode, which is pretty much a common implementation, or we can use local mode, or local MACs, excuse me, in FlexConnect mode. And that's actually our next section. We'll talk more about what FlexConnect mode is and so on. All right, so let's take a look at how traffic flows through a unified wireless architecture with CapWAP and so on. Talk about some different scenarios here. The wireless client data in a centralized architecture, a little bit more complicated than what you would see in your standalone autonomous architectures, depending on how the controller is deployed, depending on how you're managing anchor points in the network and points of attachments and so on, which we'll get into in more detail in some of our future classes. But it can be a little bit more complex. All right, the diagram here obviously does show us a couple of those different scenarios in the standard model, okay, where access points are running in local mode, which is not very common, but it can occur. I mean, well, I wouldn't say it's not very common. I say in comparison to centralized mode, local mode is not very common. But all the wireless client data traffic is going to be sent to the controller, and then the controller decides based on the policy, right? An access control list policy, a quality of service policy, how it's going to apply that information to the incoming traffic before it decides how to forward that client traffic to its final destination, okay? So when the client's wireless frame reaches the access point, what happens is the frame gets encapsulated into CapWAP, and then it's forwarded to the controller. Now this information could be encrypted using DTLS. We mentioned this previously. It's not encrypted by default, but it is something that you could add to that if you needed to. The encapsulation is true for any of the wireless LANs that are supported by that particular access point. Remember, those wireless LANs are generally tied to different broadcast domains, different SSIDs. All right, that encapsulation means that between the access point and the controller, If you're not running the DTLS encryption, you can see the CapWAP data packets that are actually sent from the AP's IP address using different port numbers, right? Actually, they're random port numbers sent to the controller AP manager address. All right. Now, again, that destination port is going to be UDP 5247. All right. Now, the return traffic that goes from the controller AP manager interface, the IP address or IP address on that interface, or the management interface of the controller, if we don't actually have a provisioned AP manager interface, again, random client port to the AP IP address using UDP 5247. Okay. Now, the details of the client's VLAN and the wireless LAN, they are actually hidden inside of the encapsulated payload, but you also have the control traffic between the AP and the controller. That's going to, again, use a UDP port 5246. All right. Now, when the encapsulated frame coming from the AP gets to the controller is going to remove that CapWAP encapsulation as well as the DTLS encryption if it's applied. It's going to make a decision on the policy to apply to that traffic, again, based on quality of service policies or access control policies. Then it's going to forward the packet to the controller's physical port that is tied to that particular VLAN for that client. Now, that's generally going to be just a port that is configured as a trunk, and then we'll just do our regular VLAN and inter-VLAN switching in the infrastructure. All right. Now, the controller's VLAN interface, which is tied to the SSID, that can also have different access control lists applied. Just like in any switch that you might have in your enterprise that has an SVI, you can apply inbound or outbound ACL rules to the logical SVI. You can do the same thing with a VLAN interface on the controller. All right. But the traffic does leave the controller from the port that's tied to that particular VLAN interface. Now, again, this logic is going to be true regardless of whether the final destination is a machine in the wired infrastructure or a device that's attached to another wireless access point, which might even go to a different controller. Even if both controllers are part of the same mobility list, and we'll talk about mobility a little bit later on, even if they're part of the same mobility list and they know the wireless clients, they have information about those wireless clients, there is no direct controller-to-controller communication for the data flow itself. Now, controllers may communicate about other events, right? There's a new wireless client attached to the network. There's tunneling for foreign and anchor configurations. And again, these are kind of some of the advanced techniques and advanced concepts that we don't get into in the ENCOR class. We really focus on those things in the enterprise wireless specialties that are part of enterprise core or CCNP enterprise. But we'll see maybe a hint of some of these things a little bit later on. All right. And then routers in our infrastructure, they're the ones that are going to be used for making forwarding decisions. All right. So let me go through kind of 3 steps here, just kind of reference the diagram points. I'm going to talk about A, I'm going to talk about B, and I'm going to talk about C. So let's start first by talking about A, right? A here, inter-controller communication, if you will. Okay. And again, these are going to be different depending on obviously the different scenarios. That's why I want to take a look at a couple of these. So when the destination subnet for a packet is the VLAN associated to a wireless LAN on another controller, the controller does not route between VLANs and subnets. So at some point, we're going to have to get to a router. We're going to use that router's routing table to decide the best way to reach a destination network. And then on the last hop to the subnet, that last hop router sends the ARP request to ultimately resolve the MAC address of the destination client. Okay. The second controller acts as an ARP proxy in this particular case. It's actually going to answer the request on behalf of the client because it knows that the client is registered to that controller. It has all of the presence information of that particular access point and client, well, client specifically in this case, so it can respond on behalf of the client. So the last hop router then forwards the frame to that controller rather than to the client itself. That second controller is what's going to take that Ethernet frame and it's going to convert it into a .11 frame. It's going to encapsulate the frame into CapWAP, and then it's going to send that frame from the access point manager interface to the AP that the client is associated to. All right. So in our diagram here, what I described is really that blue path, the kind of the darker blue path, if you will, between the two different controllers. That is kind of scenario A. Scenario B, what we call intra-controller communication, meaning that we're not leaving the controller, but in this case, we are communicating to different access points that are registered to that controller. Obviously, the flow here is going to be a little bit simpler because the clients are associated to APs, even though they're different APs, APs that are connected to the same controller. Each controller keeps a list of the clients that are associated to each AP that is managed by that local controller. If the controller receives a CapWAP encapsulated data frame from an access point after deciding, again, security, QoS, etc., the controller then takes a look at the destination MAC and the destination IP. If the destination MAC address is a client of the controller in the same subnet as the first client, then we just simply re-encapsulate that data into a CapWAP and forward it onto the AP that the client is associated to, the destination client. If the destination MAC address is not a client of the controller, or if the destination MAC address is another wireless client of the controller, but in a different VLAN, that .11 frame needs to be converted to Ethernet because it needs to be forwarded to the controller interface for that particular VLAN where the source client is going to sit, meaning that the frame is always forwarded to the controller first when the APs are in local mode. But it's never going to reach the switch behind the controller if, and this is important, if the destination is a wireless client of that controller. All right? And this logic holds fast regardless of the AP that the destination client is associated to. Make sense? All right. Rhetorical question, obviously. So the last scenario that we talk about is intra-controller, same AP. Intra-controller, same AP in this particular case. As you can imagine, this gets even a little bit simpler. All right? But even if both clients are on the same access point, traffic still has to go to the controller before being sent back to the AP and sent out to the client. All right? You might think, well, the AP can just do that local switching. But again, the APs are reliant on the controller to make most of the intelligent decisions. All right? The frame has to reach the controller because the controller is what is applying quality of service policies, security policies, and so on that would normally be tied to the autonomous AP. And for that reason, the AP could just process that traffic locally. All right? And also, we want to be able to have some visibility, quite frankly, of what's happening in the network. All right? So it's very important that you understand these traffic flows. You need to consider the placement of the controller based on these traffic flows and so on. So it's a pretty important concept. All right? So the question for this section is, which device in a split MAC architecture is responsible for .11 association and reassociation. That would be the lightweight AP. Remember, association is a real-time function. So that would be the responsibility of the lightweight access point in this particular case, in our unified wireless architecture. All right, so we'll just mark that. And that wraps up that section. Let's move on to the next section, which is FlexConnect deployments. Now, another deployment option that we have is a FlexConnect deployment, which was previously referred to as HREAP or REAP. And this is kind of an extension, if you will, of our centralized architecture. And it's primarily used for branch offices and remote office deployments. If you look at the diagram here, we see our main office wireless LAN controller. It goes to our main switch. We've got a wireless LAN link. And there is a CapWAP tunnel that is created for AP control and management. However, the client traffic is locally switched in the branch office. So if a wireless client wants to talk to a local resource within that branch location, we don't have to send the traffic back to the controller, offload that traffic from the controller into the main office location, and then in turn route that traffic back to the WAN. All right, so this is going to be a, kind of a deployment option, if you will, that is really best suited for locations with a small number of access points where deploying a controller at that physical location is really not that practical. It allows us to configure and control the APs in the branch or that remote location from our corporate office through the WAN, because we have connectivity and reachability from the access point to the controller. And then, as the diagram depicts, clients connecting to the APs at the remote location, they can authenticate locally, they can have their data bridged to the local Ethernet segment, which again we call local switching, or they can have their traffic actually tunneled over the WAN through the CapWAP tunnel to the wireless LAN controller at the central switch, and then switched off to the network, which is what we refer to as central switching. In addition to the client traffic being switched either locally or centrally, the access point can also be configured to make the decision based on the destination of the traffic itself. So it's not necessarily an all or nothing type of thing, right? We call this split tunneling. The AP can make a decision basically on what is the most efficient or most effective way of switching the traffic, rather than just kind of, completely stating or arbitrarily stating this traffic is locally switched and this traffic is central switched. All right, the AP is actually intelligent enough to make that decision. All right, FlexConnect is obviously probably going to be a good choice for small to medium-sized offices. Typically, Cisco says somewhere upwards of 50 access points at that location and below, and so on. All right. So what are the use cases that we see with FlexConnect? Retail stores, restaurants, food service locations, maybe some small warehouses. Really, honestly, any type of location that has kind of a remote deployment scenario, right? So if you have an existing infrastructure and you have a lot of locally switched traffic, right? There's a lot of communication that needs to take place locally, then FlexConnect would be your best option. If you want to move away, say, for example, from an autonomous deployment at these remote locations, that would be something to consider as well. What are some of the benefits and limitations? Really kind of all of the same benefits that you get with centralized deployments from a management perspective, and cost of use and cost of management and scalability and everything else that we talked about previously. We do have high availability and wireless LAN survivability. If the WAN goes down, the APs can kind of operate independently. It's just a much more efficient way of operating. We have wireless access and services that We can still service if the connection to the wireless LAN controller fails. Again, fast, secure roaming within the branch itself. Certainly more efficient roaming within the branch itself, as we're not switching that traffic centrally, but we're switching it locally. Dynamic VLAN and ACL assignments per user, which really is not something unique to FlexConnect. That is something that's part of the unified wireless architecture, but it's still maintained in a FlexConnect architecture. Flexible deployment and configuration options. Very simple wireless operations with data center hosted controller configurations. Again, as long as the APs have connectivity and reachability to the controller, we can manage and provision those APs from that controller. We don't need to have controllers in multiple locations. Very efficient use of WAN resources, obviously, because we can make independent decisions on how traffic is going to be switched. That's that split tunneling function that I referred to previously. Only the desired traffic is going to be tunneled to the controller, and it's very scalable. All right. Some of the limitations, probably one of the key ones, is your round trip time. Back and forth must be below 300 milliseconds. If you're running voice, less than 100 milliseconds. Minimum 500 byte MTU on the WAN. That's probably not something that we have to concern ourselves too much with in most modern WAN deployment options. And then FlexConnect also requires implementation of a site-wide VLAN for roaming to be able to identify roaming scenarios and roaming events that are going to occur. All right, so just like we talked about essentially what the data flow looks like in a unified wireless architecture, we're going to take a look at what the data flow looks like in our FlexConnect architecture. All right, so again, we did talk about very briefly the ability to do split tunneling, right? We have different ways to configure exceptions to the centralized deployment traffic patterns that we would normally see in a centralized unified wireless deployment. And the primary way we do that, of course, is to set up the branch locations to operate in FlexConnect mode. And then we can kind of establish what type of traffic is going to be switched locally, what type of traffic is going to be switched centrally, and so on. Okay? There are a few things that you have to keep in mind with this particular configuration. When you boot up, the FlexConnect AP anyway tries to reach the controller because it still has to have some sort of control function with that controller. That AP is going to obtain its configuration from the controller. So we do have to allow it to be able to initially really, be able to reach that controller for that particular reason. All right. The AP CapWAP join process, the AP CapWAP configuration process, they're not really that bandwidth intensive. Maybe kilobytes, right? Maybe 10s or 20s or 30s of kilobytes. And that's not a very good way of saying it, but and it's not really time intrusive either, right? It takes maybe 10 seconds or so, or less than 10 seconds to exact that configuration, right? The bandwidth consumption is going to depend on the discovery method that we use, and there are multiple discovery methods that are available. All right. Now that FlexConnect AP is going to keep trying to reach the controller regardless of which wireless LAN is locally switched. So even if all of my wireless LAN traffic is locally switched, I still need to be able to communicate to that controller because those CapWAP control messages, they're always going to be exchanged between the FlexConnect AP and the controller unless the controller becomes unreachable. Okay? Now that control traffic is practically almost 100% benign. You're talking about less than half a kilobit per second per AP in this particular case. Now what happens if the controller for some reason becomes unreachable? we already talked about this briefly, right? The AP kind of starts to handle all the responsibility of facilitating the client, right? The authentication, the key management, but as long as the controller is reachable, authentication is always going to be done at the controller level, all right? Regardless of whether or not you can reach the controller, there are some functions, wireless LAN functions on the FlexConnect AP that would be locally switched. So for those particular wireless LANs, if you've decided to deploy them that way, you have to specify a wireless LAN to VLAN mapping on that FlexConnect AP. Now, authentication is still going to occur on the controller, assuming, of course, that the controller is reachable. All the other traffic to and from the client, based on that wireless LAN to VLAN mapping, is going to be switched at the AP level. All right? Now, I did mention this before. You can also kind of decide from a split tunneling perspective which traffic is going to be centrally switched and which traffic is going to be locally switched. All right? But authentication, again, is always going to occur on the controller if the controller is reachable. And then how we decide to forward the data traffic is up to the configuration. All right? If for some reason I do lose connectivity to the controller, we still maintain the sessions, and we can still handle new sessions, new associations for those locally switched wireless LANs. Now, if we have defined a particular policy that says traffic is supposed to be centrally switched, for that type of traffic, that traffic is no longer going to be able to function, right? Because the session between the controller and the AP has been terminated, and there's no way to maintain that session nor to process that data. So the clients either would have to reassociate to the FlexConnect AP until the controller becomes available, or they just simply wouldn't be able to communicate. All right? Which two statements best describe central authentication on a FlexConnect AP upon a WAN failure? No new clients are authenticated. The AP maintains existing sessions and can handle new sessions. We talked about that. Existing locally switched connection clients lose connectivity and reassociate to the controller. Clients of centrally switched wireless LANs get disconnected and the client session is terminated. Yep. And that can be reestablished, of course, depending on your deployment. So those are our two choices here. Okay? All right. Now let's take a quick look at cloud deployment and how cloud deployments might change what we're doing in our infrastructure. All right. Cloud deployments in general are just basically computing on other people's computers, right? Processing, storage, etc. So the term cloud here really kind of implies the same thing. The resources that we're using, the services that we're using, they become kind of abstract, if you will. And we have a cloud service provider or some sort of managed cloud service that is providing those services. And rather than having a physical product on site, we're actually subscribing to some sort of service delivery through some sort of internet-based solution, or at least publicly or routable-based solution. All right. So the cloud itself could be off-premise. It could be a shared cloud with other customers and other clients that are looking for the same services, or it could be a private cloud deployment. It just depends on what your overall objective means. But in any event, deploying into a cloud means deploying the computer system, the network system, any kind of computing resource that would be offered typically to users would be deployed in the cloud itself. So from a user perspective, the resources are available. They don't know really where those resources exist. They don't, from the user's point of view, don't really understand where these resources exist. They just happen to be there, all right? So if I'm, for example, somebody working at home and I'm using my VPN and my software and whatnot that's installed on my computer that provides me access to all these different resources, it probably wouldn't look much different than if I was working from a computer at work or whatever, right? When we are accessing cloud resources, basically everything is going to look the same. Not completely, not entirely. There might be some minor differences with how we get access to those services, the steps that we have to go through to be able to access those resources. And that's primarily going to be based on security, right? Being able to secure access to those resources. Obviously, the security mechanisms we're going to use in a campus-based enterprise network are going to be different than some sort of cloud-based, internet-based solution, all right? But the point is that the data that the user needs, the data that the user needs to use is always going to be available, and especially in the cloud, all right? Now, the cloud itself would have to be accessed remotely, typically through some sort of internet-based solution, right? But we can also use things like VPNs. We can use a dedicated physical network to access the cloud and so on, although that's not as prevalent, all right? Computer resources that the cloud offers, gosh, there's all kinds, right? There's even different ways to provision the cloud itself. Am I offering a platform? Am I offering the complete infrastructure? Am I offering a software application? Am I offering security services? And so on. We call these as-a-service elements, right? Platform as a service, infrastructure as a service, software as a service, security as a service, and so on. But the resources could include all kinds of things: storage resources, computing resources, applications, and so on. All right. Now, the experience of using these remote resources might be different than using local resources, but I think for the most part, that experience is going to vary primarily based on how we gain access to those resources. Not once we gain access to the resources, because once we get access to the resources, they're probably going to be utilized in the same manner, right? That we are utilizing our internal resources. All right? It just depends on, from the customer's perspective, it really depends on the network access that's being used to connect to the cloud. Could be seamless. It could be always on, an always on type of connection that the client or the user doesn't have to interact with when they're accessing the resources. But it could also be something that requires user intervention to be able to activate. So you also have to consider the link capacity as well. A low capacity network link could be sufficient for services that require like minimal data transfer. They're not interactive applications. They're not high bandwidth applications. But you also might need high capacity links for those other reasons, right? The advantages to the cloud service provider based solution, cost reduction would be one of the biggest benefits, and standardization as well. Because you really are kind of talking about what we've been talking about this whole time with unified wireless is a centralized solution regardless of physical location. So we're extrapolating that same concept to the cloud as we saw with the access points and the controller in a unified wireless solution. Automation is a key to that as well. The utilization can be managed much more efficiently because we're using shared resources. We're using virtualized resources, which, by the way, can be spun up or torn down pretty quickly as well, right? So elasticity in the cloud is really, really important. The ability to change when something changes in our requirements or whatever, all right? Very easy administration. We also have fail-in-place operational models as well. We get into that in some of our other classes. The advantages to the cloud user itself, the previous ones were advantages to the provider, of course. But the advantages to the cloud users, on-demand services are available, right? We can even do self-provisioning or self-resource provisioning, self-service resource provisioning. We have a centralized appearance of all of the resources that we're using in the environment. It's highly available, or if it's designed appropriately, highly available, can be scaled. That term elasticity that I used is a common term that we use to describe the scalability and the dynamic nature of configurability of the cloud resources, and so on. All right. So CAVs, centralization, automation, virtualization, standardization, all of these things apply to things like our applications, our end user systems. These are virtualized resources, by the way. Our servers, infrastructure components, network components, storage components, and so on. All right. And quite frankly, cloud computing has several advantages over traditional computing resources. First, as an operator, the way that clouds are deployed gives you a lot of advantages, right? You have consolidation of resources. You have the ability to virtualize resources. You can automate a lot of processes in the context of cloud computing, right? You can even provide control for the end users to self-provision and self-manage those resources. They can do on-demand cloud computing, ramp up resources when they're necessary, turn in or turn off those resources when they're not necessary. All right. Now, there are concepts, of course, that are good for pretty much any IT and data center management concept, but they don't always apply to cloud deployments. All right. So even if a company doesn't plan to deploy the cloud to do consolidation, to do virtualization, to do automation, well, you know, those things, even if I don't plan to do a cloud, those things would still be beneficial, wouldn't they? We like to consolidate resources in a physical data center. Virtualization practically happens all the time in data centers today, right? Because it requires less physical resources to manage a virtualized environment. You know, less power, less HVAC, and really, quite frankly, less physical space, right? So it's not that you have to do a cloud to do consolidation, to do virtualization, to do automation, excuse me, to gain the benefit of those. All right. Clearly, if we're doing consolidation and we're doing virtualization, resources are going to be used much more efficiently, right? Virtualization of servers, which happens pretty much all the time now. You know, you might have in the past physical servers that take physical space in a rack. They have, you know, additional weight requirements, additional cooling requirements, additional power requirements, and so on. So the amount of electricity that you use, the amount of physical space, the footprint, if you will, is maybe 2 to 3 times. But with virtualization, you can take one physical server with all of the CPU power and the memory, the dynamic memory in that device. You can manage hundreds, potentially hundreds of virtual machines on one physical platform. And by the way, those virtual machines then can share those resources. And if you start to run out of resources, you can just provision or deploy more physical or virtual resources on those particular devices. All right. Obviously, in turn, more efficient use of resources has a direct cost benefit, right? You're going to have less physical equipment, so less capital expenditure on physical equipment. You're going to minimize the spending, and you're only going to pay for, going back to the cloud-based scenario, services that you actually use, right? And a lot of cloud service providers provide that granularity. You could look at it from a different angle, I guess, where the customer is offered a fixed price for each service. But the benefit of that is that now the customer knows exactly what they're paying for. They can plan their capital expenditures, they can plan their growth, they can plan the cost of that growth, the cost of doing business, and for any kind of immediate or distant future spending that they might have. All right. Now, there may be some additional education that has to take place. Users might have to interact slightly differently with the system, so there might be knowledge transfer that's required there. But again, you have to certainly identify the benefits over the cost of doing those types of things. All right. Certainly administration is going to be a lot easier. It's going to be a lot less complex, which means that staff is going to be able to be free to handle other mission critical type of things. All right. Now there is a benefit to the users of the cloud service as well. We already kind of highlighted some of those points. Centralized resources. I mean, you don't really have to have that, but in a lot of cases we actually design away from that, right? For resiliency purposes. But the resources do appear to be centralized, at least from the user's perspective. So I can move from computer to computer, I can move from office to office, location to location, and my interface and what I have available to me is the same no matter what. Okay? All data to the cloud stores will typically always be available. So users don't have to back up their data. We have backup solutions that are already deployed in the cloud, resiliency solutions in the cloud. So you might lose an important document because you might delete it or misplace it, or a computer might fail, but it's backed up in the cloud. It's like, you lose your phone.
I don't know that.
My Alexa is talking to me. You use your phone and you use iCloud services if it's an Apple phone, and if you lose your phone, you go buy a new phone and you restore from the cloud backup, right? Everybody does this all the time. And not even just Apple, everybody does it, right? Cloud computing also offers CPU and memory intensive services. You can manage those resources. Those are the resources that tend to be a little bit more elastic because your demand might change very quickly, either up or down, and you need to be able to respond to those changes. And everything is managed through some sort of portal, right? So you can kind of self-provision and self-manage in that regard. All right, so cloud offers do vary depending on what resources you need. I mentioned a few of these actually already: infrastructure as a service, platform as a service, software as a service, but there are many, many different types of platforms and many, many different types of as a service offerings that cloud service providers provide. Infrastructure as a service means that you get the network, okay? You get the computer infrastructure and maybe even a physical platform for your virtualized environment, right? So switching, routing, etc. You're responsible for deploying the physical compute resources, the virtual machines, the software, and so on. Platform as a service is something where you're provided the operating system. Our company, for example, hosts our web services and our email services on a physical server that we get access to, which is configured with Windows and Windows Server and whatnot. But we're responsible for managing that platform. We didn't have to provision the server with Windows, but we do have to update it. We do have to update the server. We do have to make sure it's secure and backed up and so on. All right. So in this case, we're delivering the computing platform and the infrastructure from a software perspective, but you're still managing what goes on to that computing platform, and even to an extent managing the operating system that it might be running on. Software as a service takes it one step further. You're going to get the operating system, you're going to get the network, you're going to get the physical resources and the virtual resources, but in addition, you're going to be provided the actual software that is needed for a particular application. Maybe it's a customer resource management platform. Maybe it's a virtual, infrastructure type of management platform. Maybe it's Citrix, or there's 100 different, or thousands probably, or tens of thousands. I don't know, different types of platforms that are deployed with software. So you can see from the diagram here, infrastructure as a service. The infrastructure that you get is CPUs, disk drives, networks, data centers, and so on. You manage the applications, you manage the data, you manage the runtime environment, you manage the middleware, the operating systems. They manage the physical networking, they manage the physical servers, they manage even possibly the virtualization of those servers, storage components, and so on. Platform as a service, the platform itself for development and runtime tools and environment. You manage the applications and the data. Pretty much the provider manages everything else because you're given the platform. You're not given the application that runs on the platform, but you are given the platform. And then software as a service, again, you're getting the application, desktop apps, mobile apps, server-based applications, customer resource management applications, and the provider's managing everything else. All right. There are other services, of course, that these service providers can provide. They can provide NAT boundaries and NAT demarcation points, if you will, to the internet. They can provide you security services, hosted collaboration, unified messaging, unified communication type of services, and so on. All right. There are many, many as-a-service models. But generally, most as-a-service models will fall under at least one of these three categories. All right? So, which cloud computing service model provides the network only? That would be infrastructure as a service, right? Now, the network could mean a couple of different things, but you're not getting a platform with iOS. You're not getting an application. So that would be infrastructure as a service in this particular case. I'm having a really hard time getting this mouse to get over there so I can mark that answer. There we go. All right. So that's obviously a very, very high level description of cloud-based services. Again, ENCOR is a lot about, a mile wide and an inch deep. So certainly there are other specialties and other courses that get into this in much, much more detail. Okay? So the next thing is really just kind of a brief discussion of the Meraki solution, which kind of is really a good segue because it is a cloud-managed wireless solution that was acquired by Cisco. So let's just talk about really kind of just the basics of the Meraki solution. Again, we're not really getting into the details here because there's a whole line of products and a whole lot of solutions that are available. But the Meraki product portfolio was acquired by Cisco from Meraki. It is a cloud-managed approach to not only managing the devices themselves, right? Provisioning devices, managing them, and so on, but deploying those devices, right? Ship and plug and play type of deployment. Okay, so you could have cloud-based controllers. You could have off-premise management for your APs and so on. Now, we're talking about this from the perspective of wireless, right? Cisco Meraki deployments provide wireless networking, in essence, as a service for clients that maybe don't have the IT infrastructure or the IT resources to manage these things in-house and on their own. All right, so if we have a really highly distributed team, we have a lean IT team, or we're just basically looking for ease of use and ease of deployment, the Meraki cloud architecture provides that. All right. It's good for mid-market businesses. It's good for remote branches that may not have on-site IT staff. Good for organizations that may already be using other types of cloud-based services and they're used to how cloud-based services are managed and so on. So that could be useful in that regard. All right. What are the benefits and limitations of Meraki? The benefit of Meraki, ease of deployment, of course, zero-touch provisioning, very, very important. I ship an access point to a site and tell the sales guy at that site, plug this into this port, right? Beyond that, the sales guy or saleswoman is not going to know what to do about configuring that endpoint. But I've already basically done the deployment. It just needs to be able to physically communicate to the internet, and then it can provision itself and do everything else. Certainly the centralized management and monitoring is a point, which is all part of the whole unified wireless architecture. BYOD support and CYOD support, choose your own device or bring your own device, because we have the ability to create these dynamic policies. Not so much a benefit of the cloud solution, just a general benefit of the Meraki solution. All right. You can do location analytics, specifically what we call CMX, Cisco Connected Mobile Experiences. You have the ability to essentially capture metrics about the wireless network. How often did a client connect? What kind of traffic did they generate? How much of that traffic did they generate, and so on. And that's where AVC comes in, application visibility and control. What applications are being used on the network? Who are the top talkers? How do I prioritize those critical applications and then limit the ability of the other applications, what we would normally refer to as non-mission critical traffic or even scavenger traffic, from affecting those critical applications. High capacity RF. We have spectrum analysis, wireless in a dense environment, of course, is going to be more susceptible to things like co-channel interference or even onboard Wi-Fi interferers or non-Wi-Fi interferers. So radio intelligence, radio frequency intelligence is going to be critical for any unified wireless deployment. You have to have the ability to understand what the spectrum looks like and how that affects our clients with their communication. Automatic RF optimization, what we would refer to in traditional Cisco Unified Wireless as radio resource management, that's going to be available. And quite frankly, just about every vendor offers some semblance of radio resource management. Now, Cisco's claim to fame is the chipset that they use, the Dave chipset that they use, and the parallel processing of the client's data traffic, and then the analysis of the Wi-Fi traffic and even the non-Wi-Fi traffic and non-Wi-Fi spectrum traffic, and to be able to process that information in parallel. So we're not taking away operations for analyzing the spectrum. Now, not every vendor has that capability, but Cisco certainly does because of the physical hardware they use to be able to capture that information. Dedicated security radios has to do, again, kind of with radio resource management, being able to identify rogues or even wireless interferers as well as non-wireless interferers and so on. Okay, some of the limitations of a Meraki deployment, you have to embrace cloud services 100%. There is no hybrid solution here. There is no premise-based solution. Not a single Meraki component is premise-based, right? Well, I take that back, right? The access points would have to be premise-based, but not managed on-premise, right? Limited customization capability. Single architecture means less flexibility because, again, you don't get the hybrid concept. You don't get the FlexConnect options. You don't get the multiple controller deployment options and so on. No layer 3 roaming. Requires site-wide VLAN for roaming. Voice over wireless LAN. Limited integration with third-party solutions. I don't know. These bullet points are definitely apt, right? They definitely are important to understand. But the key here is that you have to weigh what you're gaining from all those previous bullet points that we saw about the benefits as opposed to what you're losing. Okay? Now, just like every other model that we've looked at, we want to go ahead and take a look at the traffic flow in this particular case. How does the traffic flow in a Meraki environment? All right. So looking at the diagram here, obviously from a provisioning standpoint, the Meraki devices are going to automatically connect to the cloud over a secure connection using TLS, register with their network, and download their configuration. It's really no different than a premise-based solution. The access points are going to connect to the controller over a secure link. They're going to register with the controller. They're going to download their configuration. So there's a similarity here. The difference here is that the cloud devices don't connect to a physical controller. They're managed through the cloud, right? But the benefit is you don't have to manually stage the APs. You don't have to log into the switches for provisioning and configuration. The Meraki APs actually use something called Auto RF, auto radio frequency, to self-configure and optimize their RF settings. Very similar to RRM in the Cisco Unified Wireless environment. But again, the idea is providing the most benefit, the best performance, if you will, of the wireless network, even if you have a lot of wireless stuff happening in that network. All right. There's some out-of-band management components as well. In fact, Cisco Meraki pretty much only uses out-of-band management. So you have to use the cloud infrastructure to manage it. And I talked about that. There is no hybrid option with Meraki. All right. All right. What are the 3 limitations to a cloud-based managed wireless solution? Limited customization capability. Yep, that was one of the bullet points that we mentioned. If you have an on-site controller-based solution, you are going to get probably a lot more flexibility in how you can control that. Maybe not from a underlying software perspective, but certainly from a connectivity perspective, having the wireless LANs and the VLANs tied to the physical infrastructure. Single architecture means less flexibility. Yes, that would be one of the detriments. No layer 2 roaming. All right. Requires several VLANs for roaming across the site. Limited integration with third-party providers. Actually, that is one of those bullet points as well. And I misread the previous one of the previous ones here. Layer 2 roaming is supported. Layer 3 roaming is not supported. So we want to make sure that we uncheck that box. They got me on that one. Limited integration with third-party solutions is definitely one of those bullet points that we mentioned. And we do have automatic RF optimization, without a doubt. That is available to us. All right. All right. Now, one of the other platforms that we have available to us outside of the Meraki space, in the Cisco space, is the Catalyst 9800 series wireless LAN controllers. These are pretty robust controllers. You can see there's a couple of different ones. We'll talk about the difference between these different controllers here with this section here, but they work with iOS XE, right? They're still using all those AeroNet capabilities, but we're using Cisco iOS XE to do the integration, to manage the radios and whatnot. All right. High availability functions, seamless software updates. Your clients, in this case the APs, would always be serviced from the centralized model, right, including the 9800. The controllers have built-in security. These particular controllers actually have built-in security. Secure boot functions. There are runtime defenses that they can run. They do digital signing of images, integrity verification with hashing processes, and authentication, specifically hardware authentication. The controllers themselves can be deployed anywhere to enable wireless connectivity as long as we have reachability to that controller. Could be an on-premise device, it could be deployed in the cloud, or it could even be embedded inside of a Cisco switch, actually. All right. We can manage these controllers through Cisco DNA, which is the software-defined architecture for Cisco. We can use Netcom for Yang, more software-defined programming. We can use a GUI. We can use their command line. All right. They have a modular operating system built into them. But here's the biggest benefit, right? That operating system is open, and it has programmable APIs that enable the automation of all of those network operations with that controller. That's really the key, right? The ability to do that automation. The 9800 series controllers come in many different form factors, well, at least a few different form factors. You can use the 9800 series controller appliance. You can use the controller for a switch, which is embedded in the switch itself, or you can use the controller as a cloud-based server, cloud-based application. So let's talk about the embedded controller first. All right, we see that depicted here. The embedded wireless controller software is actually installed on a Catalyst 9300 series switch. And it provides all of the wireless controller functionality for your branch locations, for your small offices, etc., in a device that you're already purchasing to provide connectivity to your clients. Okay? So there is a limitation to the 9800 series that's embedded into the switch. On a 9300 series switch, we can only support up to 200 APs and only up to about 4,000 clients. And also a maximum of 2 controllers are enabled per site, and they would have to be enabled on different 9300 series switches. Now, if I did that, I can increase my scale up to 400 APs and 8,000 clients, which, you know, you think about that, that is not a small office or a home office, right? That is a big time deployment. So that's kind of important. All right, the 9800 series embedded controller has 2 different topologies. You can run it on a 9300 series switch, functioning as basically a co-located border and control plane device, or on a 9300 series switch as a fabric in a box. Okay? Every time I hear that term, fabric in a box, I always think of Justin Timberlake for some reason. I don't know why. Some of you might get that. All right? The embedded wireless controller deployment really supports only the SD access model, which, you know, is something that you would see typically in a highly secure environment. And the embedded controller itself supports access points, but only in fabric mode. We're not going to probably get into the details of that too much in this class, but just a point to note. All right. You also have the ability to extend the 9K services using a policy-based segmentation and using ETA, encrypted traffic analysis, to the wireless network. The 9800 series controller supports 802.11ax, as well as Wave 1 and Wave 2, actually. Seamless layer 2 roaming without having to span VLANs across devices. No need for a guest anchor. We didn't really get into the discussion of traditional mobility or traditional guest access where we're anchoring guest traffic to a controller in the DMZ or something like that. The client and AP have SSO functionality within the 9300. We can operate these as primaries, as secondaries. We can even operate in high availability mode because we can stack the devices together. What about the cloud controller? The cloud controller, as the name implies, is a device that's deployed in the cloud. This will be deployed on a Cisco UCS platform, Unified Computing System, as a virtual machine on a Linux-based operating system. All right? So it is basically like installing software. The virtual form factor can be deployed on ESXi, KVM, NFVIS, ENCS, different hypervisors. They can even be deployed in AWS cloud infrastructure using IaaS, right? Infrastructure as a service. So the cloud-based controller is not going to provide you all of the functionality that the XE software-based controller does. But it does provide some of the functionality even in the virtualized environment. If you deploy the controller as a VM, the iOS XE software functions would be deployed as if they were deployed on a traditional Cisco controller appliance. All right, so you're going to see that functionality, in other words. I guess I didn't really describe that very well, but you're going to see that functionality. So we're going to have hardware independence because we're running on a VM. Either x86 hardware, that the virtualization platform supports, sharing of resources because it is a virtual machine, flexibility in deployment, again, because it is a virtual machine. Those are the key benefits. All right. Now, you could go to a private cloud deployment or a public cloud deployment. And there are templates that you can use to deploy these platforms depending on the number of APs and clients that you have in your environment, small, medium, and large deployments. Like I said, VMware ESXi, KVM, NFVIS, and so on. All right. We do have FlexConnect and Fabric SD access deployment options. We can do small deployments up to 1,000 APs and up to 10,000 clients. That doesn't really sound very small to me. I mean, when I think of small, I'm thinking of, small business that might have 20 or 30 users. From Cisco's perspective, this is considered small, right? 3,000 APs to 32,000 APs in a medium environment and 6,000 APs up to 64,000 clients in a large environment, okay? Up to 1.5 gigabits a second of throughput, one deployment package for all the templates. Would just be really a matter of how the resources are allocated. When you instantiate the VM, you're going to identify what type of deployment you're doing. It's literally a radio button that allows you to pick which deployment option. And then everything gets provisioned based on that. All right, so there's a bootstrap available. You install the VM, you go through the process, and it's going to have all the recommended parameters. Lastly, you'd have branch optimization by deploying the 9800 CL as your virtual machine, even on a Cisco 5000 series ENCS or Enterprise Network Compute System. A little bit different than UCS, but you're going to be running the NFVIS. Public cloud deployments, again, I can read these bullet points here, but it is an infrastructure as a service solution using the 9800 CL, CL standing for cloud, which is available in the AWS marketplace, Amazon Web Service. Supported only with managed VPN, Cisco FlexConnect central authentication, and local switching are supported. It's actually pretty good, right? We talked about the FlexConnect modes a couple sections back. Up to 3,000 APs and 32,000 clients. And then again, we're going to instantiate that 9800 CL in a virtual private cloud. All right. The 9800 embedded controller is only supported in which deployment model? We actually talked about this in kind of right at the beginning of this section here. It is only going to be supported in the SD access, right? Let me see if I can find where that was. Right here. Right here. The embedded wireless controller deployment model supports only SD access. Oops, let me scroll up here. I'm talking like I'm showing you, but I'm not showing you, right? Right here. Where is that at? Right here. The embedded wireless controller deployment model supports only SD access. Okay? So the answer in this one would be SD access. Mouse keeps disappearing. Don't know why. All right. So we have one more section left, describing Cisco Mobility Express, and then we're going to get into our summary challenge, and then we're going to wrap up this lesson. So the last thing we're going to talk about here is describing Cisco Mobility Express. Now we could actually spend really several days talking about this particular topic. And again, that's not really the goal of Enterprise Core. It's really just to give you a general understanding of basic deployments, deployment options, basic architecture options, and so on. There are specific wireless specialties that get into much, much more detail on these particular topics. So Cisco Mobility Express is a way for us to provision solutions for branch offices, small to medium-sized businesses. You want to have a managed AP solution without having to buy or maintain or even manage a separate wireless LAN controller appliance, right? So Cisco Mobility Express is basically a virtual wireless LAN controller that's integrated on the access point itself. All right. So interestingly enough, all access points run AeroNet CapLab images. And they actually acquire the wireless LAN controller functionality, which is the Cisco Mobility Express image that needs to be installed on the access point. And in this case, by the way, that would be it would have to be 802.11 AC Wave 2. This is not supported on other standards. All right. So there's two components to this functionality. You have what we call the master access point, and then you have your subordinate access points. If you've worked with Aruba, for example, this is a similar type of concept, right? It's a virtual controller running on an AP. Obviously, the master access point is the one that runs the virtual controller, which is why it is called the master. And depending on the model, that access point can manage anywhere from 100 access points below or down and up to 2,000 clients. All right. And then, of course, it's an AP as well. So it can also service clients as an access point. Certainly the subordinate access points themselves, which would be just the access points that are managed by that master access point, these are deemed the subordinate access points. And they can only service clients. They're not going to run the wireless LAN controller functionality. Those access points can be 802.11c Wave 2, but they're not required to be 802.11ac Wave 2. So what would be the benefits of running Mobility Express based on this brief introduction? Simplicity. You can deploy access points very quickly. You can troubleshoot, you can manage, you can set up multiple sites, you can set up mobile applications, web UIs, Cisco Prime, Cisco DNA Center, and so on. Very, very cost effective. No controller. No access point license costs, because when you buy a controller and you provision a controller, there's licensing that has to be purchased for that. No subscriptions. You can reuse the same access points. Maybe connect them to a physical controller if you decide to move to a physical controller function. Functionality, central authentication. You can do local switching, open wireless LANs, WPA2 PSK, WPA2 Enterprise with 802.1x is going to be supported. Guest VLAN with central web authentication using a captive portal. Local web authentication using a captive portal. You can even customize the internal and the external splash pages that are going to show up. Again, support for layer 2 mobility and layer 2 roaming. We've seen this multiple times, right? Layer 3 is where we get problematic. Layer 2 is generally going to be supported. Detection of failed master access points and the ability to fail over to another master access point, and so on. All right. Now the book does kind of get into configuring a master AP. I guess I can kind of go through these bullet points. Number 1, power up the master AP by connecting it to your PoE switch or some sort of power cube or external power source. Once the AP is booted, it's going to broadcast the Cisco Air Provision SSID. By the way, this is the same kind of process we would use to provision access points to a geographical region. This could take up to 10 minutes, the book says. Connect your Wi-Fi enabled laptop to that Cisco Air Provision SSID. Enter the password and the username. Well, just a password, I guess. Open the browser to mobilityexpress.cisco.com and then go through the setup. So it's not quite plug and play, but it is very, very close. Which type of access point must the master access point be? 802.11ac Wave 2. All right. All right, let's wrap up this section here by talking about or going through some of the summary questions. So the first question, in which 2 situations would you deploy an autonomous AP? Rapid expansion, probably not going to meet that requirement, right? We have to have flexibility and we have to have the ability to expand quickly, hence the term rapid. Autonomous isn't that, right? Small distributed branch offices. Yeah, that seems like a place where I might decide to run an autonomous AP. Certainly not a large branch office. Maybe a small isolated warehouse as well. Okay. Which 3 of the following correctly describes the benefits of a centralized controller-based wireless solution? Easier to deploy and manage than autonomous APs since the APs in a centralized architecture function independently. So most of that sentence was correct except for the last part. They don't function independently, they function as a group. All right. Better control over client parameters, absolutely. Centralized control, but to me that would be better control as well. All right. Better roaming capabilities, yes, because we have access points that have the ability to identify one another as well as communicate to one another. That's going to lend itself to a better roaming environment. Scalability is going to also increase as well. Okay. Less risk of traffic bottlenecks. Actually, that's the opposite, right? You do have the potential for bottlenecks. Which three statements correctly describe the benefit of Cisco FlexConnect? Local switching? Yeah, absolutely. That's one of the choices. Central switching or local switching. So locally switched traffic per wireless LAN. Absolutely. Functions during a WAN outage. Yeah, I didn't mention the name of it before, standalone mode, but I did indicate that that was something that was available. Remains functional for a configurable amount of time during a WAN outage, fail-safe mode. No, that doesn't apply because we're not limited to the amount of time we can run in fail-safe mode. Branch guest access with WebAuth. Yep, that's definitely something that we would support. WebAuth is kind of like a captive portal type of environment where you're capturing credentials that were either provided to the client or they're putting their information in. Coordinated central and local wireless LAN controller operation. No, the benefit of FlexConnect is that you don't have to have both central and local wireless LAN controllers. In which cloud service model are applications managed by the provider? Well, that provider is providing you software. Right? If it's an application, it's software. That provider is providing you software, so software as a solution would be applicable there. Which deployment option does the 9800 Cloud Wireless Controller provide for a private cloud support? That's actually the only one that provides everything. Right? So Centralized, FlexConnect, SD Access. All right. Which statement correctly describes the Meraki cloud managed solution? User data flows to the cloud controller? No. User data does not flow to the cloud controller. That wouldn't be very efficient. Supports layer 2 roaming only. Yes, we mentioned that specifically actually in one of the downsides to the Meraki solution. I don't really want to get into the reason that is. That's a little bit protracted, that discussion, but it is definitely a limitation. What are the licensing costs for Mobility Express? 0. Yeah. There are no licensing costs for Mobility Express. You're already paying for the licensing for the switch. So they're not going to get you twice. Okay? All right. That concludes that entire section there. We will be seeing you guys in the next section. In the next section, we're going to talk about wireless roaming and location services. And then we have 3 more after that. Wireless AP operation, wireless client authentication, and troubleshooting wireless connectivity. All right. And by the way, we will be getting into some discoveries as well. We don't have a discovery until we get to the authentication. We'll be doing Discovery 18. Then we have a second discovery, Discovery 19, for troubleshooting. So we only have a couple of discoveries in the wireless piece. So we'll take a look at location services and roaming services, and then we'll get into AP operations. See you guys there.